Hello, my name is Larissa Falkington, and this video will be an introduction into the basics of lens aberrations of microscope objectives. Aberrations are errors in the objective lenses that occur as a result of artifacts that arise from the interaction of light with the lens. There are two main types of aberrations. One is spherical and the other is chromatic. However, field curvature is another common aberration seen in microscope objectives. With spherical aberrations, the light rays passing through the peripheral of the lens are brought into focus at a different focal point than those passing through the center of the lens. This is caused by the peripheral rays being refracted to a greater degree, while the center rays are refracted only slightly. The difference of these focal points can be seen in this diagram. As a result of the differences in refraction, the image being viewed becomes spread out rather than being in sharp focus. This image here demonstrates how this affects the focus of the image so that the entire image is unable to be viewed at one time. The Gaussian lens equation is used in relation to spherical aberrations in order to determine the relative locations of images formed by a curved lens. This can be used to account for the discrepancies in focal points caused by this aberration. In this equation, n refers to the refractive index of air, n prime is the refractive index of the glass lens, s refers to the object distance, s prime is the image distance, and r is the lens radius. The second major type of aberration is the chromatic aberration. Chromatic aberration occurs due to the presence of various wavelengths of light present in white light. As white light passes through a convex lens, these various wavelengths are refracted based on their frequencies. This is referred to as dispersion. Blue is refracted to the greatest extent, followed by green light, and red is refracted the least. This image shows the various focal points that the different colors are refracted to. Due to this dispersion of the colors, each wavelength has a slightly different focus point, which results in colored fringes around the image. As you try to focus on one color plane, the image becomes fringed with the other colors. This can be seen in this image, where the black horse is fringed with the various other colors. The majority of lenses used in laboratories today have objective lenses that correct for these aberrations. For example, when two lenses, such as crown glass and flint glass, that each have different refractive indices and dispersion properties, are melded together, they are able to bring blue and red wavelengths to a common focus point near the green wavelength. This lens combination is known as a doublet and is found in achromatic lenses. Furthermore, fluorospar can be introduced into the glass fused from the lenses, which enables the red, blue, and green wavelengths to be brought into a single focus point. This lens combination may use three lenses melded together, known as a triplet, and these types of lenses are known as apochromatic lenses. This image illustrates the differences between the lens groups in achromat and apochromat lenses. It may also be noted that another lens known as a semi-apochromat or a fluorite lens exists, which has slightly less correction than the apochromats, but more correction than the achromats. Another aberration is field curvature. Field curvature occurs as light is focused through a curved lens, which results in the image plane being curved as well. This means that either the center or periphery may be in focus, but not the entire specimen at one time. Field curvature aberrations are corrected using flat field objectives. These objectives are referred to as plan objectives and are usually applied to lenses that have already been corrected for chromatic aberrations by adding more doublet and triplet elements that result in an image that is mostly flat. These objectives are known as plan achromats, plan fluorites, and plan apochromats. This table summarizes the types of objectives that are available to correct for spherical aberrations, chromatic aberrations, and field curvatures, and to what level they perform these corrections. Plan achromat is considered to be the best type because it corrects these aberrations the best, as it corrects the most colors in spherical and chromatic aberrations, and it corrects for field curvature. Achromat lenses, however, have the least amount of correction. To conclude, spherical aberrations, chromatic aberrations, and field curvature are three of the most common aberrations in objective lenses. Once these aberrations have been corrected, an image may be viewed for the